Hey Keith, do you know what this is a picture of?
I feel like you ask this question a lot.
Hey Keith, do you know what this is a picture of?
This looks like my great uncle Albert's handlebar mustache. Is that what it is?
Hey Keith, what do you think this is a picture of?
It looks like a low resolution picture of an alien summoning his troops from the earth. If you can see the way his arms are kind of arced up there.
Seriously though, can't you see the speckle and the specular reflectors?
Oh, yes, I see them now. This is a brain, isn't it?
This is an ultrasound picture of a brain. Yeah, okay. So today we're going to talk about ultrasound imaging, and the outline for our talk today is imaging basics. So we already just had a whole lecture on transmit and transducers. So we're going to talk about the imaging aspects here. And we're going to talk about speckle and where speckle comes from, some useful tricks in ultrasound imaging. Some of it will be useful to us. On the transmit side, very useful for ultrasound neuromodulation. And last year when I gave this lecture, I said the receive side is not so useful, but interesting nonetheless. And I went through it. And actually, I'm going to change that. So the next lecture after this one, we're going to talk about functional ultrasound. And there, the imaging is all done on the receive side with the receive beamforming. And so kind of getting an understanding of how that works is actually going to be maybe useful for the next lecture. So although I said it's not really useful to us, I'm going to take that back.
Yeah, I would take it back in even a couple ways. Like we've seen grants and proposals for using imaging within a transmit probe, like in a therapeutic probe as well, too, right? I mean, it's starting to happen.
Yeah,
So
absolutely. That's absolutely right. A lot of ultrasound devices for therapeutic ultrasound have in this like a ring array that's the therapeutic part, and the center part is an imaging part, right?
yeah, so we'd be depriving you if we didn't teach you a little bit about imaging, and I think it'll be useful nonetheless. I agree with you, Kim.
Okay, all right. Well, let's now just get into last year's lecture on ultrasound imaging. Okay, we're back, and this time we're going to talk about ultrasound imaging. So how are you doing today, Keith?
Great, Kim. And I wanted to start off today by asking the question that everybody always asks me, and I'm sure they ask you. When you're imaging a fetus and a pregnant woman, what's going on? Is there enough ultrasound power to get neuromodulation that we're going to be talking about in this class?
It's a great question. All we really know is that when we are scanning the fetus, we are at power levels that are way below the threshold for any kind of damage. And so we'll talk about that in the next lecture. What are those thresholds for damage? But we're below those when we're scanning, and it's a very similar power to level to what we're doing with neuromodulation. And so we don't really know. We could be stimulating the fetus.
Yeah, I remember reading from the Gavrilov text that some of the earliest reports of neuromodulation were just doctors holding up, the ultrasound probe to the stomach, and then the fetus would start kicking. And anecdotally, they notice this all the time. So I have to ask you, Kim, fact or nah?
We don't know. We do have to talk a little bit about some of the confounds. So a little bit later, we'll talk about the auditory confound, for example. And then you might ask, well, is the fetus hearing something? But let's talk about that in a later lecture.
Super interesting. So anyway, back to imaging.
Yeah, okay, so let's talk a little bit about the imaging basics, a little bit about speckles so you know why the images look the way they do. And then I'd like to talk about some useful tricks in ultrasound imaging, some of which will be useful to us. Those are the ones that are used on the transmit side. And then a little bit of some useful tricks on the receive side. They're not so useful to us, but they are interesting nonetheless. So that's my outline for today. So let's get started about imaging basics, and I'll start out with a linear array, and a little bit later I'll talk about the phased array. We talked about this last time when we talked about arrays, is that you have an overall aperture, and there's some number of elements, they have some width associated with them, and then the distance between the elements is the pitch. There's some height associated with them. You use some number of elements. Now, of course, this transducer shown in this cartoon has very few elements. Usually it's something like 128 elements or something like that. And so then you use a subaperture, meaning you use some subset of these elements in order to create a beam. And then you image the echoes that are coming back from that beam. So of course, this is the axial direction, this is the azimuthal direction. Okay, so that's what we talked about last time. We didn't really talk too much about the elevation direction, which is sort of like the slice thickness direction. And typically you use a lens in front of the transducer elements in order to do some focusing in that direction. And so that's the basic idea. So when you scan multiple lines to interrogate the whole scan plane, and you'll do one line after another. Here they're kind of spaced out. Of course, we're not actually going to do that where they're spaced out. We're going to do overlapping beams, and then they're going to be much closer together so you don't see any gaps. And we get an overall scan plane that looks something like this. So of course, because just like in the in-plane direction, that when you look at the slice direction, there's going to be a focusing effect, so that there's going to be a part where it's thinner, and that's going to be the focal zone in the slice direction as well. And so
How popular are three-dimensional images if you had a bunch of linear arrays? Does that happen a lot, or do people always use these single row transducers?
Are you asking about three-dimensional imaging?
Yeah, is that popular, or does it exist? I mean,
Yeah, well, there's a couple ways you could do it. One way is you could set up a 2D array, and then you can do some beam formation in the slice direction as well as in plane. So that's one way to do it. To do that 2D array, you'd end up with a pretty large transducer. It's heavy for the technologist to hold. There's a lot of wires and a lot of going into it. Another way to do it is to take a 2D array like this one, and then to set it up in a system so that you could swing it back and forth and get multiple lines that come out sort of radially from an axis point. And then as long as you know where the handle is, like you could put some markers on it, and if you knew where the handle was, then you would know where those planes were, and then you could just interpolate into a 3D grid.
interesting.
So, yeah, no, it's a good question. All right, so let's get back to how we do this. We're going to do multiple lines in order to get a scan plane, and this is how we do it in 2D. So we've talked about our subaperture to focus in the in-plane direction. We use the lens to focus through the elevation direction, and then we use multiple lines that are going to be overlapping to get the whole scan plane. So each time we do this, we send a beam out using our subaperture. There's going to be some reflectors in the beam path. You're going to get echoes that are going to be coming back from those reflectors. You'll get the echoes coming back from the near ones first, the farther ones later. And what you're going to get is essentially something that looks like this. So this is your time signal. You convert the time signal into a distance, just using the velocity times time over 2, because it has to go there and back. Gives you the distance or the depth of that echo, and that's called the range equation. And it always is going to assume the velocity of 1540 meters per second. So once you get that and you convert it into distance, now what you have is basically one line of your image, and then you're going to repeat this by translating over your subaperture, acquiring multiple lines, and then building up your image that way. The image is going to look like this. You see there, you can basically see the little pulses in there, and it's a whole series of the transducers up here above. It's a whole series of little pulses that are coming back, and these ones that are at depth are coming back later, and the ones that are more shallow are coming back earlier. So the basic idea is then you're going to do this multiple times. So you're going to pulse, you're going to listen. You have to listen long enough for the echoes to go to the farthest depth and then back again. And then you can translate your subaperture and do another line, and then et cetera, until you've gone across your whole field of view. And then you come back and repeat with that field of view again. All right, so let's look a little bit at the timing. You can't transmit and receive at the same time. So you transmit and then you listen for the echoes to go their farthest distance and back again. So the time for an individual line is 2 times the maximum depth that you want to acquire, divided by the velocity. So in this case, let's say you have a 20 centimeter depth, then the time for a single line is 40 centimeters divided by 1540 meters per second is about 260 microseconds for that echo to go to the 20 centimeters and back again. Seems like it's pretty fast. Then you might ask, well, how many times can we repeat that per second? Well, if it takes 260 microseconds per line, then you just say 1 over 260 microseconds per pulse. That gives you something like almost 4,000 pulses per second. And this is called the pulse repetition frequency. If you're going to repeat those pulses as often as that, and of course you're going to translate over your subaperture and get line by line, repeat it, and have a particular frame rate, when you repeat it, the frequency that you repeat the pulses is called the pulse repetition frequency.
Yeah,
So that's
I
going
have a question. Is this restriction of time really because the transducer will naturally move from the technician? You know, if the transducer were perfectly still, would time be an issue?
well, you assume that the transducer is still. And so when you translate over which subaperture you're listening to, that's just done electronically. There's no movement at all.
But if the subject is moving underneath the transducer,
Well, so
you
it's an interesting point, because it turns out that the pulse repetition frequency is really high. And then you say, well, how many times can you repeat that? Well, it sort of depends on what field of view you're using and what depth you're using, but you can certainly get frame rates that are on the order of 30 frames per second, or sometimes even higher than that. And of course, if you calculate the frame rate, being 1 over the time for a single frame is going to have number of lines times the time for a single line. And then that's going to be now given by this equation. So it depends on the depth as well as your field of view and how many lines. But you can easily get frame rates at about 30 frames a second. And so that's sort of considered real time. Somebody's moving, they're not going to be moving fast enough that you can't kind of image that. The fastest motions are really kind of the valves in the heart. And ultrasound is a great way for imaging the valves in the heart. You can do that with frame rates about 30 frames a second, or you can actually change this up a little bit. So instead of getting an image, what you can do is you can interrogate one line repeatedly over and over again, and that's called M mode. And if you put that one line right through the valve, then you can see that valve motion at very, very high frame rates. Okay, that answers your question?
Absolutely.
Okay, so you're going to get an image, looks something like this. These are the individual echoes that are coming back. You see it has positive, negative, these are little cosines. This might be, you know, one part of a larger image that looks something like this. And then you look at this and say, how do I convert that to something that's a little bit more usable? And so the way you do that is basically converting those cosines or sines into the envelope. Because the RF image with those positive, negative little sinusoids isn't really all that useful, but the envelope is what we're interested in. So a couple ways you can do that. First of all, you take your sinusoid and you rectify it. So that just means you take the absolute value. So all these negatives will now become positive. And you get something that looks like this. It still has these lines in it, which isn't all that kind of satisfactory to look at. So something else you can do is you can come by and you can smooth this line. So use a low pass filter. So just smooth the line, you get something that looks more like that. And now you can see something that looks more like a traditional ultrasound image. So you can see that there are these areas which have high echo signal coming back, and they're going to have this envelope is going to be really high, and you get this bright blob right here. Bright blobs, and you have dark blobs. And then this right here is a cyst. So it's like a bag of fluid. And there isn't anything much that's going to give rise to echoes from the bag of fluid. And so it's going to be really dark in there. So that's called anechoic, which means no echoes coming back. So there's a number of different ways you can do this image formation, going from these RF signal to something that's smoother and looking at the envelope. And I've just told you the low pass filter because it's really kind of conceptually easy to understand. There's harder ways to do it that are, you know, give you different image quality using Hilbert transform and things like that. But I don't really want to get into it right now. I think that this kind of gives you the idea of how it's done. Okay, so this is an example image. The transducer in ultrasound imaging, it's always as if the transducer is above and you get the picture coming down from the transducer. And it's interesting because no matter what the orientation is, the body, it could be different orientations. It could be a longitudinal view, it could be a transverse view, but the picture is always going to look the same, so as if the transducer is up above. And then the image looks as if it's like this. So it's one line coming out from the transducer, multiple lines making up the image. What you see is the speckle pattern right here. So this looks like it's liver. You see speckle in the liver tissue. You see this right here, which is the specular reflector. You remember what this is, Keith?
You mean like what organ?
Yeah.
Is it the diaphragm?
Yeah, good, right. Because you're going to get 100% reflection in an air tissue interface. And the liver is right up against the lungs. So if your transducer is at all pointing towards the lungs, then you're going to get 100% reflection right at that interface, which is where the diaphragm is. So diaphragm is just a muscle that overlays the liver, between the liver and the lungs.
And Kim, we're
So
seeing parts of this image are a little bit outside of the focal zone, or is this just entirely covered by a long focal plane?
I'm not quite sure what your question is there. So here's a transducer. There's going to be a beam that comes out and it's going to have a focal point. This one isn't annotating where the focal point is. It's going to be kind of converging towards the focal point where the beam will be the thinnest, and it'll be diverging from the focal point. So if you look at it, you can actually see the speckle pattern gets a bit bigger in the very far field. And you see the resolution looks like it's the best up here. So that's where the focal point it probably is. I'll talk a little bit more about focal zones in just a moment. Some other things you can see, so there's the speckle pattern in the liver. You can see these areas where there's no speckle pattern, so that's a cyst right there. It's a large cyst. There's not only is there nothing in there, nothing much to give you echoes coming back, so you don't see a speckle pattern, but there's also no attenuation, so that if you look at the signal beyond the cyst, then you see it's brighter than the signal that went through liver tissue all the way. So this hasn't had the attenuation, whereas this tissue has. So what that means is,
acoustic window, right?
yeah, well, that's the idea, right? What it means is that the properties or how bright the signal is, what you see is due to the tissue itself, but also due to the beam path. So that's something to think about that's a little bit different than other imaging modalities where what you're seeing is really just due to the tissue and not due to the beam path. You can use this concept exactly like you said at times to image something with high signal beyond a bag of fluid. So I think we talked about this before, where the bladder, for example, could be used as an acoustic window so that you get high signal beyond that. And that's called posterior acoustic enhancement. Makes sense. Okay, so there's an example image. That one didn't have any annotations. This one has a lot of annotations. So here's a picture. This is somebody's abdomen. This is part of the liver right here. I'm not totally sure what all these other structures are, but what I really wanted to do with this picture is just to walk you through some of the annotation. So up here at the top, there's a couple of terms that we haven't had a chance to talk about yet, but these are definitely going to come up in the next couple of lectures. So there's mechanical index and thermal index, and both of those have to do with your pulses. The mechanical index has to do with sort of the intensity of the pulses, and the thermal index has the ability to raise the tissue any amount of temperature rise. And so that has to do with the intensity of the pulses as well as how rapid they are. So we'll be talking about those definitions just a little bit later. The blue ones have to do with sort of the transmit side of things. So this one talks about the probe. This is a curved linear. These letters don't mean anything to me, but this particular scanner type has a probe, which they call it this number. There's some other things here. So the fact that it's an abdomen is something the sonographer might type into the computer, and it just sets up some presets. So it probably sets up something like maybe the field of view and the depth and what frequency to use and things like that. And then the sonographer has an opportunity to manipulate those, but this just sort of sets up some presets. Right here we have the frame rate. So this is a pretty good frame rate, 24 frames a second. So as a person's breathing, and they're probably, you know, continuously breathing, the liver might be moving in and out of the scan plane, but because the frame rate is so good that each of the individual images looks pretty sharp still. There doesn't seem to be much motion blurring. It's B mode image. We might have a chance to talk about non-B mode imaging a little bit later. Frequency, so this is much higher than for most of our therapeutic applications and higher than the transcranial applications, this one being 4 megahertz. Let's see, depth over here. So this is specifying the total depth. And when you type in a depth of 14 centimeters, what that's doing is telling the computer how long to listen to that echo coming back before it goes and does another line. So 14 centimeters is the longest time that you're willing to listen to the echoes coming back. Some other things here, transmit power. This right here is the focusing depth. So there's a knob on the scanner that tells the computer where to focus. And remember, there's going to be some subaperture, and there's going to be some phases across the subaperture in order to set up the focal depth. And so this is just telling some annotations saying where that was set up. This is just a length scale, these dots saying it's in centimeters. And then there's a little bit of, in green is things that are set up for the image display. We don't really have to get into those too much. So that's a typical image. Any questions about that, Keith, or shall we move on?
No, look good to me.
Okay, so how is imaging done? So we're going to send out a pulse. The echoes are going to come back. We're going to listen to all those echoes until that farthest one came back. And then we're going to do it again. Just as we mentioned, those echoes are coming back. When it came back from the farthest distance, we do it again. So some other definitions. Pulse repetition time. So we send out a pulse, we're listening, and then at some point we go translate over our subaperture and we send out another pulse. The time between those pulses is the pulse repetition time. 1 over that is the pulse repetition frequency. All right, spatial pulse length. So let's talk about that. It's the number of cycles within your pulse times the wavelength. Okay, Keith, you know I'm going to ask you this one. We have 1.5 megahertz beam. What's the wavelength?
Sorry, what was the 1.5 megahertz?
Yeah.
Is it like 4 millimeters or something?
Okay, now remember, so when you multiply the frequency times the wavelength, you're supposed to get something that's about 1.5. So the frequency in megahertz and the wavelength in millimeters, you'll get something like 1.5. So okay. It's about a millimeter. Okay, so maybe this one will be easier for you. What's the spatial pulse length? If you assume that the number of cycles is 3.
Spatial pulse length for 3 cycles. Let's see, 3 millimeters?
Yeah, good.
God, I got that one. That's embarrassing.
All right, so that's spatial pulse length. And remember that the spatial pulse length plays a role in the axial resolution. So we'll see in a little bit how that plays a role. So resolution, there's axial resolution and there's lateral resolution. Axial resolution is just the ability to distinguish objects that are within the beam path, within the line in the axial direction. If they look as if they're on top of each other, then they're not resolvable anymore. Lateral resolution is the ability to distinguish between objects that are perpendicular to the line, the direction of the ultrasound beam. All right, so let's talk about axial resolution. You have maybe 2 objects. There's going to be an echo coming back from the first object, an echo coming back from the second object. And if the computer sees them as different, then they're resolvable. If the computer sees them as overlapping on top of each other, then it's just going to look as if it's one big blob and it's not resolvable. What you can do if your 2 objects are closer together and you want to be able to resolve them is you have to make your spatial pulse length smaller. And you do that how? Keith?
Less cycles or better or shorter ring down time, like higher Q, maybe?
Well, those will do the same thing. The shorter ring down time with a lower Q would give you fewer cycles. Yeah. Or you can change the wavelength. So you can use the higher frequency to lower the wavelength. Now your pulses have a smaller spatial pulse length and they look as if they're separate, and now you're going to be able to resolve those objects. Okay, so what exactly is the resolution? Let's say you have two reflectors that are separated by a distance of x. You're going to have two echoes that are going to be coming back. The separation between them now is 2x, whereas the separation between the two reflectors was x. Now you need to make sure that 2x is greater than their spatial pulse length. So 2x needs to be greater than n lambda. So now just solving for the limit of your resolution is where x equals n lambda over 2. That's the smallest object that you're going to be able to resolve.
Kim,
So
can you
yeah.
remind us why we wouldn't just go to an extremely high frequency to just resolve everything better?
Yeah, great question. And for ultrasound imaging, there's always the interest in going to higher frequency for better resolution. But then there's this trade-off when you want to image at depth, because there's going to be more attenuation. And so you're constantly struggling between, I want resolution, so I want higher frequency, but I want depth, so I need lower frequency. So basically you use the highest frequency that the depth will allow you to use. Okay, so just some examples, 3 cycles, frequency 1.5. Our resolution now is about 1.5 millimeter. If you go down in lower frequency, then what you see is the resolution gets to be pretty terrible. So most of diagnostic ultrasound is about 1 megahertz and higher. Smaller fields of view, smaller depths allow you to go much higher, and the abdominal imaging is often around 1 megahertz. Okay, so we've talked a little bit about speckles so far, but let's talk about it a little bit more so you have a better idea of where that comes from, because then I want to talk a little bit about brain imaging. So there's an image, nice picture of the liver, very similar to what we saw before. We've got that nice specular reflector. We see over here, these are hepatic veins that are dumping into the vena cava. And one of the nice things about ultrasound images is there's often a lot of annotation in the images, which is great. Here it tells you it's the liver. It tells you it's a transverse view. It's on the right side. So that's pretty nice to have all that information. Okay, so there's the intensity of the speckle changes with the tissue, and it provides diagnostic information. In other words, it provides the ability to differentiate between tissues. So for example, if you have a bag of fluid and you know it's a cyst because you can look at the speckle pattern. Sometimes if there's a cancer, you might look at it, it might have a different speckle pattern than the liver, it might not. So there is sometimes the ability to use the speckle pattern for diagnostic information. Hyperechoic means there's more scattering. Hypoechoic has less scattering, and anechoic has essentially no scattering.
And scattering here is equal to more speckle. That's the general
That's right.
relationship?
That's right. And so then you might ask, well, what exactly causes the echoes to come back? What's giving rise to the echoes that then gives rise to speckle? Because speckle is just an accumulation of signals from multiple reflectors. Let me try to say that in a different way. So your tissue is made up of lots of reflectors. Something like collagen within the tissue is going to give rise to a tiny little echo that's going to come back. And you have lots and lots of collagen molecules in here. Well, let's say we look at one line through the image, and maybe it looks something like this, and let's split it up into a number of different voxels. And within each voxel, you're going to have some number of echoes, some number of reflectors. They're going to give rise to echoes coming back. In the adjacent voxel, the reflectors are going to be in a different spatial pattern, and so on. Each voxel is going to have a different spatial pattern of reflectors. This first one is going to have 4 echoes that are going to come back. They have, because they're in different distances from the transducer elements, they're going to have different phases when they come back. So there's going to be an interference pattern from each of those 4 reflectors. The interference pattern could be constructive. They might all add up to give you a very bright signal. Then your speckle pattern is going to be very bright. Or maybe it's destructive, and maybe there's phases that are kind of in and out of phase that are different phases so that they are destructively interfering with each other, and then the speckle pattern is going to be dark. So the speckle pattern really has to do with the fact that these echoes that are coming back within a single voxel are sort of randomly placed, and you're going to have different placement of the reflectors in each and every voxel. It's a variable pattern of reflectors, and that's going to give a variable interference pattern and a variable intensity to the signal that comes back and is picked up. Well, so Speckle is often viewed as useful, provides diagnostic information. Sometimes it's viewed as not helpful. Like if the speckle pattern is bigger than differences between the different types of tissues that you might be able to pick up otherwise, then oftentimes people ask, well, how can we reduce the speckle? Ha, are you interested, Keith? Because there are ways to do that.
I'm very interested. I think I was supposed to ask how we can reduce it. This might be. How do we do it, Kim? How does this happen?
All right, so we're going to do this multiple times, and you know, the adjacent line to this one is going to have a different speckle pattern because again, these reflectors are random in the tissue. The adjacent line to that is going to have a different speckle pattern. So if you were to image not these exact same voxels, but maybe voxels that come in from an angle, then you would see a different speckle pattern for that same point in space. And then if you average up these different signals from the voxels that are slightly different because they're at different angles, then you might be averaging out that speckle pattern. Okay, so let's just review just for a moment so we're all on the same page. How do we get lines that come in at an angle? Well, so we talked about that before in terms of transmit, where let's say you have a subaperture and you have your wavefront. If they have all the same phases, your wavefront comes out, you have a linear wavefront, you're going to get a beam, but you can do better than that by phasing them around a circle. You can steer them to the side by adding a linear phase so that there's a linear phase to that linear angle to the wavefront that steers it to the side. You can, as I mentioned, have the wavefront come out so that the wavefront follows a circle and it's naturally going to get focused. And now you're going to see a thinner beam, and then you can apply those together. All right, so we talked about that before on transmit, gives you different beams in different directions. Well, you can apply those same concepts on receive, which is really interesting, right? If you want to receive from this area, then when the echoes come back, you're going to phase them. Well, in this case, we didn't do anything special to the phase. If you want to be sensitive to a beam that comes back from an angle, when those echoes come back, you're going to add phases to those echoes in that same pattern that we talked about before, so that now when they add up, they're going to give you a beam sensitivity that looks like this. Just like on transmit, we're going to add phases to change the beam sensitivity on the receive side. Same thing that we can get a better receive sensitivity on in terms of the focusing, you know, the lateral focusing, if we use phases that follow that circular pattern, and etc. So same thing that we talked about before on transmit in terms of applying those phases. Well, now we're going to apply them on receive in order to manipulate our receive sensitivity. Okay, so that's how spatial compounding works, is that we're just going to get the same image, or we're going to get the data, and we're going to manipulate the data differently. So we're going to combine, you could do it on the transmit side by getting 3 separate images. That would reduce your frame rate. You could do an image like that, you know, an image here and an image there. That would reduce your frame rate, as I mentioned. But you can also do it on the receive side so that you're sensitive to, you know, taking that same data. You can manipulate the data so that you're sensitive to the data along a line that comes straight back, or along a line that comes at an angle or at a different angle. So this is the single image, and then we're going to compare it now to the spatial compounding. So now this one has the extra receive phases. So, and then those images are now added together. The annotation is slightly different. The frame rate actually is the same because this is done on the receive side.
So Kim, can you explain that a little bit more? Does that mean that you're only receiving one signal and that you're applying a phase and that changes the angle? So it's just like mathematical operations, but no more than one image, really?
Yeah. So on the receive side, you can receive all the data, and then you can apply the phases to your subaperture to be sensitive to the line that's straight down. And then you can make up the image that way. And then you can say, well, let's take that same data, change the phases on our subaperture so that now we're sensitive to a line that comes in from the side. So,
And do those usually have the same quality, or is there any reason that one method is better than the other? You know, multiple frames versus just a mathematical approach on the receive side.
well, we'll see, what you can see right here is that we're getting rid of some of that speckle pattern. And so the goal is to have a better quality image with less of the speckle.
Oh, sorry. I mean, one method to do the compounding is to take 3 images with different
Mhm.
transmit angles, and then one is
Mhm.
just to edit the received data or
Mhm.
that phase. So is there a better method between those two?
Well, it's probably better to do it on the transmit side, but then you sacrifice frame rate. To
Right.
get the same image, if you have to do it 3 times over, your frame rate is 1/3.
Okay.
Okay. So let's talk a little bit about brain images. This is not something that's done very commonly because we need an acoustic window. It turns out the newborn gives us an acoustic window because you can't image through the skull because the attenuation both ways is really high. And so the different plates in the skull in the newborn haven't fused yet. And there's this area here called the fontanelle, which is just soft tissue. And so you can see it right there where the fontanelle is. It's always kind of interesting with a new baby that you're always very careful of that spot, always kind of like very nervous because there isn't any skull to protect the brain. But anyway, it does give us a nice acoustic window. So here's an example image that was acquired through that acoustic window. And it's really interesting to kind of look at it. And I'm going to go to the next slide to compare and contrast with a T2 weighted MRI of a newborn. And so what we see with the T2 weighted MRI is we see areas that are bright signal. And so what that's telling us is areas of fluid. So this is CSF and the ventricles right here. There's CSF here that bathes the brain all around. And so this is what we're used to seeing, and thinking about the CSF means it's a pocket of fluid. The T2 bright signal is a pocket of fluid, right? So here with the ultrasound image, of course, if it's a pocket of fluid, we're going to see dark areas. So that's what we see up here in the ventricles, is an area that's really dark. But down here in the area where we're used to seeing CSF and used to thinking that as a sort of a bag of fluid, it's now very bright. And so that's a little confusing. What's going on here, because we usually think of the CSF as anechoic, but here in the sulci, it seems to be hyperechoic. And if you look at the anatomy, then what we see is that in the subarachnoid space, there's fibrous bands in there. And those, remember we were talking about what gives rise to speckle, that there's echoes that come back from collagen. Well, the same thing here is that they're going to give rise to echoes coming back, these thick fibrous bands. And so what we see is that there is actually a speckle pattern, even though there's fluid in there and a significant amount of fluid that gives rise to bright signal in T2 weighted MRI. Here it's going to be bright on the ultrasound images because of that fibrous tissue. So it's nice because then it kind of gives an outline of the sulci, and so you can see, sort of the anatomy of the brain. A little bit different than we might expect. So it's nice to kind of take a look at it and understand it a little bit.
People
Of
actually
course, ultrasound imaging isn't something we can do typically in adults or even older children, just because of the skull, because of attenuation, which we talked about at great length already.
Mhm. What would people use it for with the child, to look for like gross brain abnormalities, like just some sort of small brain or swelling or
Oh,
something?
yeah. I mean, if there's like a tumor, for example, and then the structures are off to the side, you can see that kind of thing. No, I'm not a radiologist. I don't know all of the uses for it, but there definitely are uses for ultrasound in newborn imaging. Okay, so let's see. We talked about the basics of ultrasound, the linear array, and some speckle discussions. I want to just talk about some useful tricks in ultrasound imaging, and some of which will be useful to us for our neuromodulation goals. So we talked a little bit about multiple focal zones. Again, the idea is that you're going to use a subaperture and you're going to put the phases such that you're going to focus at a particular point in the image. If you want to focus to a different point in the image, then you might use a different set of phases so that now the beam is smallest at that second focal point. And you can get multiple images at different focal depths and combine them all together. So this image over here, there's multiple focal depths and it's combined so that it should have better resolution throughout the image. Whereas here, this is gonna have the best lateral resolution here, the best lateral resolution down here, and this should be better throughout. We do see that the frame rate is decreased. Although, oddly, I'm not quite sure why. There's 1, 2, 3, 4, 5 focal zones and the frame rate is only decreased by a factor of 4, not 5. So there's something I don't quite understand there, but it's close.
Also, the image, it doesn't really look that much better. We used to have this problem back in the day. Kim would show these two pictures. She'd be like, you can clearly see on the right that this image is much better axial and lateral resolution. And I just can't really see it.
Okay, well, let's take a look at it just a little bit more carefully. I think right here on this inclusion, you can see that this bottom edge is sharper than the top edge.
Oh, that's true. That's true.
Okay, all right. And so the bottom edge, which is sharper, is closer to the focal zone than the top edge. And so you might ask if the opposite is true over here, because it should be that the top edge is sharper. Well, it's certainly sharper than it was over in this image. By moving the focal depth up, we certainly have sharpened up that top edge. And then on this third one over here, it seems like both edges are sharp. So I don't know, have I convinced you now?
Yeah, a little bit more. I guess I was looking at the speckling too. It's interesting you get less speckling in focal zone 2 here, you know, in the middle region.
Yeah, so this isn't really supposed to address the speckle. This is supposed to address resolution and loss of resolution because
and
of
I
the
guess
beam.
the poor resolution is almost like applying its own like low pass Gaussian filter to the image and smoothing it out. But yes, that the image on the right does, I'm seeing what you're saying here.
Yeah, it's low resolution because the beam is wide. And so your voxel is big and there's an averaging. Yeah. Okay. All right. So multiple focal zones on transmit. You maybe use a smaller subaperture for acquiring one image, a larger subaperture for another image, and another subaperture that's larger. And so the beams from each of them is going to be a little bit different and focusing at a different point. I mean, if you look at the width over here on the third subaperture, the widest subaperture, you can see that it's a little bit more narrow than it is here on the most narrow subaperture, which seems to be wider way out there. So you can, that's just how you do it, is you use a different subaperture on transmit, and the number of different depths that you use is going to cut your frame rate by that number of depths. It's going to give you a better lateral resolution. There is going to be a trade-off between resolution and field of view because we can only image from the center of the beam, and then as we translate over our subaperture to the other side, we have to go to the last line that we get, and then that's painted on the image at the center of the beam. So when we use a larger subaperture, we narrow up our field of view. These edge elements help to give us that beam, but we don't get a line of the image from each of those edge elements. So there's a little bit of a trade-off. More resolution you want, the larger your subaperture, but that's going to give you a smaller field of view. All right, well, here's another trick. We talked about this before, where we talked about an array as being a series of elements, and each one is a rectangle. So that means because of the rectangle, we get an overall sync envelope in terms of our beam. And then we talked about before having a rectangular weighting function across the aperture. Well, here what we've done is now we've applied a Gaussian weighting function. So there's still a rectangle, but you can reduce the amplitude of what you send out on the edges so that the power that's sent out from each of them is reduced, so that you have basically a Gaussian function, envelope function here. And then when you Fourier transform that to say, what does the beam look like in the Fraunhofer zone, Now, each of these individual points is no longer a sink, but is now a Gaussian. And so what we've done is we've basically gotten rid of the side lobes. And so it sort of can clean up the image a little bit. You still have the grading lobes, but it does clean up the side lobes. And here's what the math looked like. So here the envelope was the Gaussian, and then wave forward transform, now we have a convolution with individual little Gaussians. So, so that's kind of a nice trick, and it's something that we could use in our application in therapeutic ultrasound. If we have an array, we can use a weighting function in order to get a cleaner beam without the side lobes. Okay, so this is really cool. And this is something similar to what we saw before, where those same concepts that we applied on transmit before in order to get 3 beams, well, you can apply now those concepts on receive. So you've already sent out a beam, and now you're going to receive, you want to receive from an area that's sensitive, has this sort of sensitivity, then these are the elements you're going to listen to. Now echoes are going to come back from a little bit further away. You're going to listen to a larger aperture, to the elements across a larger aperture, so that from those echoes that are coming further away, you're going to get a thinner beam, essentially, and so on. So the latest echoes that come back, you have the largest aperture that you're listening to, you phase them appropriately, you're going to get a nicer beam in the far field. So that's really kind of a neat trick. This is called dynamic receive focusing. Because on receive, why choose just one focal depth? You know, you can just keep on changing up your aperture so that you can dynamically have a larger focal depth on the receive side. It improves your images.
Is it electronically inexpensive to listen if we're trying to make a low power device? It's really the transmit that burns a lot of the power, right? Uses a lot of power.
Yeah, right. You're gonna put power in on the transmit, and then on the receive side, the echoes are gonna power up the piezoelectric crystal, because it's the echoes that power.
You have to individually amplify every signal, so maybe that's expensive. I'm wondering, you know, why wouldn't we always be receiving on all channels, you know, or more, at least using this technique, and maybe we are.
Because mostly what neuromodulation is done with right now is with single elements. And when we start moving into arrays, it's time to start getting more complicated. All right, so here's just some examples. If you transmit beamforming only, then there's an area that's going to give you a nice focus. This sort of seems like an extreme to some of the simulations I've done. The focus is pretty sharp here, pretty divergent in the far field. And what you see is that you're really only getting a good focus right at the focal depth. And then if you do the dynamic receive beamforming, then you can be sensitive to a beam which is much thinner across the length of it. And now you can see that you have a much better image, in that you can actually see structures that you weren't able to see before. Maybe you combine that also with the weighting function and et cetera. So maybe it gets a little bit better. All right, and then the last topic here is the phased array imaging. So this is, you know, pretty much the same thing we talked about before. We're going to slew the beam off to one side. We do that, we've got the phases that give us some focusing, as well as a linear phase that'll slew the beam off to one side. We've got the phases around a circle that will give us good focusing at the depth that we desire. Without the linear phase, then you go to the other side with the linear phase. And so that's how you slew the beam. And in the case of the phased array imaging, you use the same elements for all of the image. It typically has a smaller transducer, and all of the elements are used, and then you slew the beam side to side. And this is used in times when you really have a small acoustic window. So in the case of liver imaging, oftentimes you might be placing the transducer between the ribs, for example. And so you might have a very small acoustic window, and there might be shadowing from the ribs on either side. And it's nice to be able to get a beam, a picture, which is bigger than the acoustic window. So it's like a small acoustic window, and the beam diverges with the phased array imaging And so that's why that's so powerful, is that you can really, see a much larger area than that window might have suggested. All right, so let's wrap up. Unless you have any other questions before we wrap up.
Question that I don't know if people are thinking it, but if you look at an MRI compared to an ultrasound, it's just, I mean, they're almost not comparable in image quality. In MRI, you can see so much more detail. So what are the main reasons that people are still using ultrasound? And obviously it's still heavily used today.
It is cheap and easy. You compare an MRI system, which costs millions of dollars and is not portable. It's huge. It has very major sighting constraints, to a very portable ultrasound system that, sometimes you can, it's on a cart, which is relatively big, that moves around. But some of the newer systems are, plugged into an iPhone and has a little transducer. Cheap
Butterfly
and easy.
IQ, I think, right? Is that what it's
That's
called?
right. That's right. I mean, ultrasound is incredibly powerful for the size and the expense.
And can you tell me, you always tell me this interesting number, the radiation that you would get from, actually, yeah, how much radiation would you be getting from like something like an MRI or a CT?
Oh, so radiation comes in when we're talking about CT. With
Not
MRI,
like an MRI. Okay.
not so much. But let's talk about that later.
Sorry, I'm just so interested in
All right, so let me just remind you what we talked about. Imaging basics, we're going to get echoes that come back from depth. They're going to give us an RF image that looks like this. We're going to look at the envelope of each of those, make it up an image. What we're going to see in the image is a lot of speckle. We talked about where the speckle came from. We talked about tissues that are going to have bigger reflections, some are going to be smaller, and then that gives rise to diagnostic information. And we talked about some useful tricks, such as increasing the size of the aperture so that we have a narrower beam. You can, of course, do that on transmit, and you can also do that on the receive side. Some really fun tricks there. So that sort of wraps up our ultrasound imaging lecture. All right. That's it for today.
Thanks, Kim.